Hello everyone, this is Ruiqi from the UC Berkeley NLP group. Today I'm going to talk about pseudocode-to-code generation, and this is joint work with Mitchell Stern and Dan Klein. In this work, we generate code from pseudocode, which means mapping from the box at the top to the box at the bottom. The code comes from online judges such as LeetCode or Codeforce. Our goal is to generate executable code that can pass the test cases. On average, there are about 15 lines per program, and the longest is 400 lines. It is challenging to learn an end-to-end model. Here is a naive method to solve this problem. It first translates pseudocode into program fragments independently line by line, and then directly concatenate them to form a full program. Unfortunately, this naive approach does not work. The reason is that pseudocode has language ambiguities, and its interpretations depend on the context of the program. For example, there are two interpretations of the pseudocode let ch be the start of s. It can be declaring new character variable ch and set it to the value of the first character of s, or simply setting the value of an already declared variable. Choosing between these two options requires the program context. We need to use syntactic and semantic constraints to disambiguate. In this presentation, we introduce a method to search for high-quality programs by combining program fragments under syntactic and semantic constraints. We start with a simple baseline and gradually add components to it to reach the final version of our method. As a warm-up, we first describe the baseline that generates and combines program fragments independently from each line without constraints. Then we discuss the syntactic and semantic constraints we will impose when we combine program fragments, and we use beam search to find such combinations. At last, we propose scaffold search to improve speed and accuracy. We first search for valid scaffolds, an abstraction of the syntactic and semantic information of the program, and then combine program fragments based on the scaffolds. This approach can be viewed as a form of dynamic programming method, as a scaffold abstracts away the minimum information needed to verify the constraints from each program fragment and avoid computing and verifying similar constraints by memoization. We use a standard sequence-to-sequence model to generate multiple candidate program fragments for each single line of the pseudocode, each associated with a probability score. For each line of the pseudocode, there are multiple plausible candidates, either due to language ambiguities or model uncertainties. For example, in line 1, the pseudocode is main function starts here. The model is pretty certain that the corresponding program fragment is int main. In line 5, the pseudocode is let ch be the start of s. It can potentially declare a new variable, or simply setting the value of an already declared variable. y51 is the highest scoring program fragment for the pseudocode input at line 5, and let p of y51 be its probability score. Analogously, y52 is the second highest scoring program fragment for line 5. After we have generated the program fragments and their scores for each line, we can have a matrix view of the program fragments. In this table, each row is a line of the program, and each column is a program fragment of that line. For example, the three entries in row 5 are the three program fragments corresponding to pseudocode on line 5, which were shown in the previous slide. Program fragments are the basic units that we are going to work with, and we assume this matrix of fragments are given. Throughout this work, our goal is to search for some combinations of the program fragments to form a program, which is equivalent to selecting a column for each row. Additionally, the score of a program is given by the product of scores of individual program fragments. Let us see some concrete examples. We are showing an example combination of program fragments where we select one column for each row. So here are the actual program fragments. We concatenate them to form an executable program. The baseline approach solves an unconstrained optimization problem of maximizing the score of a full program by selecting a column for each row. As a sanity check, in this setting, the highest scoring combination is obtained by concatenating the fragments in the first column, and its score is given by taking the product of the score in the first column. The top k highest scoring combination, or say, the top k highest scoring program, can be generated efficiently using a priority queue. Now we look at the accuracy of the baseline approach, where we do not impose any constraints when we combine the fragments. It does pretty poorly, and in particular, it achieves 0% top 1 accuracy. We need constraints to select and combine program fragments. On the left is a full program candidate formed by the selected fragments, and on the right are other unchosen fragments for each line. On line 5, the selected program fragment redeclares an already declared variable, hence making a semantic error. We should have selected other fragments for this line to satisfy the semantic constraints. On line 6, the selected program fragment has an extra trailing open curly brace at the end, hence making a syntactic error. We should have selected other fragments for this line to satisfy the syntactic constraints. Therefore, we need to enforce syntactic and semantic constraints when combining the program fragments. Here is how we are going to enforce syntactic constraints. We parse each program fragment into grammar symbols. For example, line 1 of the fragments int main parenthesis open curly is parsed into return type function name parenthesis and open curly. To check whether a fragment combination satisfies the syntactic constraints, we concatenate the grammar symbols and check whether it is a possible derivation from the abstract syntax tree grammar of the programming language. We use color green to denote grammar symbols. We can also enforce semantic constraints on the program. We extract which variables are declared and used for each fragment. For example, line 2 of the fragments int n ans equals 1 declares new variables n and ans. We keep a variable table to check whether any fragment redeclares a declared variable or uses an undeclared variable. We use color purple to denote variable usage and declaration information. Remember that our goal is to solve a constraint optimization problem of finding the top k highest scoring combinations while satisfying the syntactic and semantic constraints at the same time. We use beam search to find such combinations. We now look at the performance of our constraint search method. Being seen means using beam search under syntactic constraints, and seen plus sem means syntactic and semantic constraints. We find that adding syntactic and semantic constraints consistently improve program accuracy. However, we swept something under the rug here. We were unable to obtain the top 1000 accuracy with a naive beam search method. If we're considering the top 1000 combination, the beam width needs to be at least 1000. The time complexity of naive beam search grows quadratically with beam width, hence making it impractical. How can we improve the search speed and save computation? We look at the program fragments and find that many of them share the same grammar symbol variable usage and declaration. For example, for the 2 program fragments in line 1, they are both simple one-line statement that declares a variable I. For the 2 program fragments in line 2, they are both using variable I and does not declare new variables. They are exactly the same in the eyes of our constraints. But in the regular beam search method, we have to check whether the constraints hold for all 4 possible combinations, which are in fact the same. A lot of computes are wasted here. Therefore, instead of directly verifying constraints on the program fragments, which is on the left, we actually want to abstract away the information needed to verify the constraints from each program fragment and check constraints only on those abstractions which are on the right. We call those abstractions scaffold. Here we formally define what is a scaffold. We define the scaffold fragment of a program fragment to be the grammar symbols plus variable declaration and usage, which are the information needed to verify the syntactic and semantic constraints. We use color pink to denote a scaffold or a scaffold fragment. In other words, pink equals green plus purple. We can combine scaffold fragments to form a scaffold of a full program, just as we can combine program fragments to form a full program. We can directly verify the constraints on this abstraction called scaffold, and it satisfies the constraints if and only if its corresponding program satisfies the constraints. In other words, the brown box satisfies the constraints if and only if the pink box satisfies the constraints. Our method first search for scaffolds, which is now on the left, and then filling the scaffolds with program fragments to form actual executable programs, which is now on the right. Because our approach searches the scaffold first, we need a way to obtain the scaffold fragments and their scores. At the top of the screen are 3 program fragments for the same line, along with their probability scores. We marginalize program fragments that have the same scaffold fragments. In other words, the program fragments that are the same in the eyes of our constraints. The score of a scaffold is a product of individual scaffold fragments. Now we have set up the stage for scaffold searching. We want to combine scaffold fragments from each line to form a scaffold. We know how to check whether a scaffold satisfies a constraint. We also know how to score a scaffold. So as before, we can use beam search. But there is a huge difference from before. Since we're now searching on the scaffold, which is a form of abstraction, there are much fewer possibilities, so we can use a smaller beam size. We are also saving computes for the similar constraint verification, so the beam search is faster. Remember that our goal is still choosing one program fragment for each line to form a full program. So here's how we are filling the scaffolds with program fragments. We only consider program fragments that agree with the scaffold fragment for each line. Any program fragment combination satisfies the constraints if the scaffold is valid. We can efficiently generate top K programs given a scaffold. Now we look at the results. We use beam size 50 for scaffold search under syntactic and semantic constraints and beam size 200 for the regular beam search. With scaffold search, we obtain better accuracy with smaller beam size. Scaffold search allows us to calculate the top 1000 accuracy as well. To conclude, modeling fragment dependency is key to achieving high accuracy. Adding syntactic and semantic constraints improves accuracy significantly. Scaffold search saves repetitive computations and increases speed and accuracy.